All right. In this part, let's take a look at matrix sketching, which is employed as a mechanism within Patch2Self. Before we get into matrix sketching or constructing core sets, let's look at what the backbone of Patch2Self really is, which is overconstrained least squares regression. So this is the basic formulation of a least squares regression problem, where you have your data and you're trying to minimize the uh, L2 norm, right? And this is a massively over-constrained problem, at least in the case of Patch2Self, where your number of rows, that is n, is much greater than the number of columns in your data, right? So in Patch2Self, if you recall, we had all the voxels or all the patches flattened out along the rows, and each column corresponded to a different gradient direction, right? And we are solving this in a self-supervised fashion. And if you had, let's say, 64 gradient directions, you would be repeating this 64 times, which is quite time consuming and in fact even memory intensive, given that you have to store all these voxels in memory. The way this problem is typically solved is by projecting the B onto the column subspace of A, right? So you want to project this B and solve it iteratively on that orthogonal subspace that you'll build using the Moore-Penrose pseudo-inverse. This is typically done using one of the three type of solvers, depending on what type of A you have, right? So if your A is well conditioned, then you can use the Cholesky decomposition, where you decompose it into an upper triangular matrix R. If your matrix is rank deficient, then you can use a QR decomposition. And Q is nothing but the orthonormal basis, meaning that each column in the Q would be orthogonal and normal, like summing up to 1. And if your matrix A is L conditioned, then you have to resort to a singular value decomposition, where you will get a solution even if it is an L post problem, right? And in this case, you have your left singular vectors, right singular vectors, and your singular values. In the case of Patch2Self, it is typically either rank deficient or L conditioned, and we recommend using one of these two solvers, both of which have been made available in Dipy via scikit-learn. So why do we need matrix sketching? So when I say over constrained, it means that the number of variables is much lesser, the number of unknowns is much lesser than the number of equations, right? So the number of columns is much lesser than the number of rows, which means that you have multiple possible solutions in this so-called tall thin matrix or over constrained problems. And you can think of the rows as constraints to solving your least squares problem. So you want to reduce these constraints, rather pick out a subset of rows or transform the rows in such a way that it approximates the original problem. So when you do so, you are going to go from a dimensionality of n cross d, where n was much greater than d, that was your original problem, to r cross d, where r is now the reduced subset or the compressed matrix, such that R is more or less of the order of D. So let's say in Patch2Self, if you had 1 million rows by 64 columns, now you can go to the order of maybe 1,000 rows by 64 columns, right? And that's why this approximately sign. And obviously, when you do so, you're not going to be getting the exact solution that you would get out of a least square solver, but you will get terribly close. And this epsilon is basically the failure probability. It's accounting for that. The main two advantages of constructing this core set is that you will do faster regression, meaning that Patch2Self will be really fast, and two, it would be low memory. So instead of having to load 1 million voxels in memory and training this regressor iteratively multiple times, now you will have lesser memory since it is just a 1,000 by 100 matrix, let's say. There are two popular ways of constructing this core set, at least via matrix sketching. The first one is by preconditioning it with a random matrix. And this is a toy figure that I've shown over here. So let's say this was your random matrix. A random matrix means nothing, but every entry in this row or column is sampled from a random, like from a standard normal Gaussian, right? So this is a completely random matrix where every entry in every row has been sampled from a standard normal Gaussian. This is your data matrix A. I just represented it in the column format. And you can think of like performing this dot product operation where you now get a low dimensional representation of what was your n cross d. Now you will get it in a k cross n, right? This relies on the Johnson-Lindenstrauss lemma, and it has different names. Like, for example, some people refer to this literature as random projections, but in general, you're just preconditioning your data, and then you're doing the regression on that data. So that's why I call it preconditioning. But what we saw in our work, which is soon to be published, is that sampling and rescaling using leverage scores actually works better. And this is what I will be focusing on in the coming slides, although I will be showing comparison against these type of methods. So let's look at leverage score based sampling and how you can use that to construct matrix core sets. right? So let's say this was your actual data, the same problem. You have an over-constrained problem with n much greater than d. Now you want to pick out particular rows from this matrix A, right? And the way to do that is by using a randomized probability distribution, and you want to pick out the same rows from the matrix A and B, so that you can solve the problem, right? And so this R1, R2, R3, Ri are the rows that you will be sampling. And once you sample and rescale, you will now get a much smaller sized matrix A, which would be similar, like what I explained in the previous slide, of dimensionality where R is approximately equal to D, right? So the leverage score sampling algorithm, which was proposed by Patch2Self and Soda in 2006, basically follows this approach. You take a bunch of probabilities, which are based on leverage scores. Bear with me, I will talk about leverage scores in the next slide. But you use these to sample basically rows from this matrix A. Then you pick out these rows, and you choose these rows in a probability from 1 to R into P. That is a probability. Don't worry too much about this. It is just to make sure that the probabilities are in the range 0 to 1. You rescale them, and then you solve that induced subproblem. Induced subproblem is nothing but a smaller regression on a smaller matrix. So what are these leverage scores, right? These leverage scores are nothing but the row norms of the U, that is the left singular vectors. So we know two things after we do an SVD. So let's say this was your data A. You got your U, sigma, and V, where U are your left singular vectors, V is the inverse like the transpose, and sigma are your singular values. You know that the columns of this U are pairwise orthogonal, but you also know that the row norms are somewhere between 0 to 1, right? And those are nothing but your leverage scores. So your leverage scores are literally the row norms, like the squared row norms, and this is nothing but a normalization factor. And that's it. So basically what we are saying is that when you sample and rescale this matrix, your almost orthogonal representation is now going to be represented, your orthogonal representation, which you got from your SVD, is going to be represented as an almost orthogonal representation by choosing this row subset. So let's see how this works within the Patch2Self framework. Let's say you had your diffusion MRI data, where I've just shown in Q space, each point corresponds to a different gradient direction. You construct a Casarati matrix, like we did in Patch2Self, where each column corresponds to all the voxels that you extracted or patches that you extracted, right? Now, you want to construct your sketched matrix, which basically has only a subset of the voxels from your entire Casarati matrix A, right? And you do that by either doing random projection space sketching or the leveraged score space sketching that I talked about right now. Now you get a sketched matrix C, which is much smaller than your actual Casarati matrix A. A Casarati matrix is nothing but essentially a linear difference matrix where each column is obtained independently. And then you run Patch2Self again on the smaller Casarati matrix. And surprisingly, your denoised output looks very similar, which we will look at in the next slides. But before we start looking at results, let's take a look at how these matrix sketching methods compare against one another. So the one that you see on top is the deterministic leverage score. So deterministic leverage scores means that instead of randomly sampling based on the leverage score probability, we deterministically choose how many, like the top 100 leverage scores or top 1,000 leverage scores, and all the way up to 100,000, right? The uniform is just uniformly sampling different voxels. The randomized leverage scores are the ones that I just explained, where you compute the leverage scores for all voxels, and then you choose the ones which are like you choose randomly based on those leverage scores. Then you have count sketching, which is another type of sampling and rescaling method. And then there's the subsample randomized Fourier transform, or it is also subsample randomized Hadamard transform. I've used a Fourier transform in here. And you see that more or less all sketching methods at some point start flattening out and converging at around 100K, right? And we saw that randomized leverage scores actually performed better. To evaluate the speed up empirically on my standard i7 laptop, we see that like on simulated data, you can get up to like 3 times speed up on a 64 direction standard DTI protocol. You get a speed up of around 3.5 times, and on the standard for Hardy data set, you get it up to like 6 times, right? approximately a sketch size of 10,000 is generally sufficient, and I'll talk about how to choose the sketch size. But my point over here is that as the size of the data set increases, the speed up that you will get will be much higher. So for example, if you had to run Patch2Self and Patch2Self sketch on, let's say, the HCP data set, the difference is going to be of the magnitude of 10x. Right. So now, how do you really choose this optimal sketch size, right? So we have a method based on QR decomposition where essentially we iteratively only once iteratively choose the sketch size to denoise one gradient direction, and we use that same sketch size for all other gradient directions, right? So the sketch size is nothing but checking how independent, like rather the update of the sketch size is checking how independent are the columns based on the number of rows that you select. And we get this nice elbow plot where essentially you can see here that after 12,000, approximately 12,000 rows, the gain that you get from adding more rows, or rather sampling more rows, is not really useful. And this is done on the basis of a QR, like the rank revealing QR. And yeah, basically you see that the error between these two is not really very high. It's of the order of 4, which is not much for diffusion data, where the original range was from 0 to 4,000. Now, looking at simulated data, you see that Patch2Self sketch or Patch2Self 2 come very close to Patch2Self, meaning that the performance, there is no loss in performance, right from SNR 15, 20, 25, 30. I've quantified that in a table. We also quantified this on microstructure and tractography analysis. So for example, on top that you see is the raw radial kurtosis from that CP70 dataset. After Patch2Self, a lot of these degeneracies were reduced. And with the sketching-based Patch2Self, also these degeneracies are gone. And same is the case with the tractography data. You see that there is no loss of information or no noisy artifacts are added, and we show that with ODFs. So here you see the corpus callosum bundle, and on top you see the optic radiation bundle. Lastly, and this is one of the key findings of when we were playing around with leverage scores, which is why we also think it is a much better tool, is that leverage scores actually provide a noise metric in the sense that leverage scores back in the 80s were actually invented to do outlier detection, right? So they are revealing which voxels, in this case voxels, but which data points in your regression problem are going to affect the regressor very heavily. So which have a higher leverage on fitting your data, right? And implicitly, by the setup of Patch2Self, you can actually get points of high leverage, and they are very much revealing of the nature of noise. So for example, at the bottom, if you see the PPMI dataset, you can see that there are areas in the center of the brain where noise is much more susceptible and can really deviate the denoiser a lot more, right? Whereas if you see in the HCP70 dataset, you see this banded pattern, which is actually shown by the leverage scores. And we have seen this even in the denoising example that I showed in the previous presentation. So basically, I will be elaborating more about how you can evaluate this noise in better ways. But this, the 3D leverage map is also equivalent of what one would get from a standard deviation map from, let's say, MPPCF, right? And let's look at this in detail in the next